the radioactive isotopes, what do you use it for? Use it in what? Dyes, right? So these dyes, you need to prep your patient before using the dye. So 24 hours before, right? A low carb, low sugar. Pretty much they tell you don't eat anything after 10 or after 9. And then no vigorous exercise the day before. And then 6 hours before, of course, you cannot eat at all. So that's what they say, after 10 p.m., don't eat anything. I mean, you can have probably a little juice, but nothing before 6 hours. The day of the blood sample, what are you gonna do? Oh, they take blood samples, they take glucose levels, and what they do is they deliver it by IV, this dye. And the dye, what it does is like it reacts with the PET scan, which is actually it's a CT scan that just gets its magnetic resonance around the body of the person, and this dye just emits a light. So this takes about what, 60 minutes, and the scan is about 20-45 minutes scan. So it's a full body scan in this case. Okay, so that's what we use most of the time on the clinical field, radioactive isotopes. So once you get that, you can actually get something like this. You get your radioisotopes, which you can see that they're actually lighting up around here, and that's something that it's not supposed to be there, right? Because everything else looks fine except that mark. So that marking tells you what? That there's some sort of a problem in there. Let's call it a problem. So the other one that we use it for also as well is that the most type of radioisotope that is used, or the most common one, is the technetium-99, and is actually, of course, this is the medicine that deals with this radiation, right? The use of radioisotopes is called nuclear medicine, and it provides images all the way through the body. This one is in a transplant patient. Normally, this transplant patient, what happened is that if you look, it has a blood flow, and you can see that there is actually blood flowing and all that red markings, correct? Now on this side right here, look, there's no blood flow there. So that means somehow there is a problem. So there is a problem in the circulation. So all we do with this one is, well, in this patient, you can see that there is an issue on the apex of the heart. On the other side, we have a bypass. So normally, this is the blood flow, right, which is diminished. You can see that there, right, because it's supposed to be red, not yellow. And then when you do the bypass surgery, in other words, you craft a new vessel to the area of the apex, then you're able to get what? Blood flow back. So we use this pretty much almost all the time. Now, if you do a scan of the brain, you can see that everything is fine except that thing right there. It's that blue mass right there. So that tells you is a what? This is a PET scan, but is a spot for a brain mass. Well, they already know it's a tumor, but it's a brain mass. So that's the use of it. And of course, we also use this for radiotherapy. Again, it's a high radiation, X-ray or gamma rays. Of course, these are neutrons, protons, right? And other sources that tend to help us in the what? In the kill against cancer. Now, this is the old way of doing. Nowadays, at the beginning, they said you have to do a radiotherapy and then chemotherapy, order chemotherapy and then radiotherapy. And then they decided that no, the best thing is to combine both, to do chemo and radio at the same time at a low dosage so you have less side effect in the body. The whole point is that when you give radiotherapy, which is X-rays, heating your body, whatever that mass is located, it not only affects the mass or the cancer cells, but affects all the rest of the tissues as those rays hit the actual mass. So if your liver is in the way, guess what? You're going to damage your liver. If your skin is in the way, guess what? You're going to damage the skin. If your blood vessels are in the way, guess what? You're going to damage the blood vessels, and so forth. So this is pretty much like trying to kill the cancer with a hammer. In other words, like you have cancer inside, I'm going to hammer your whole body. In other words, so it actually damages the whole tissue, right? We're still not there yet. The last thing that we have for treating cancer is using our own immune system. So we get us a cancer sample, we prep our immune system, lymphocytes, and it's actually called immunotherapy, which is you get your own antibodies, you put it against an antigen, and now they're able to fight cancer. I mean, your body's not gonna kill your body. So they're just gonna bind to the actual cancer cells and they're gonna try to kill it. Now they've been working on this for quite a while, already for about 7 years or so. Now it's actually more freely available to everybody. It's about $10,000 per each session. So that's that. Now the main thing that you need to know here is the energy levels. And 1, 2, and 3, you can have infinite numbers of shells. The main thing that you need to know is that on the first shell, you're going to have how many electrons on the first shell? 2. First shell can only handle 2, and everything else can handle up to what? 8 electrons. Does that make sense? Now, let's say, for example, you have how many protons? 1, right? 3, there's 6 total, right? Everybody agree? Okay, cool. I know how to count. So if I were to make this atom stable, how many electrons should I need? 6. So let's fill them up based on the rule that I already gave you. So fill them. How many electrons in the first shell?
2.
Let's draw 1 and let's draw 2. On the second shell, how many electrons? 4. Why 4? Because you only need 6, right? You can fill up to 8, but you only need 6. And so far, so good. So that's the hardest thing here. Now, the electrons, as far as they move outside, like to the outer shell, that means what? The energy level is going to be what? Higher. So as you move from the center to the outside, the energy level of that electron is going to be greater. If by any chance, instead of having 6, I have 7, that means what? I have unstable molecule, correct? Right. Awesome. And then those, first shell 2, 8, 8. You can see that there. So normally we have an atomic number, right, of 18 for argon. And then how many protons? 18. How many neutrons? 18. And normally you should have the same amount of neutrons and protons for this case. And then, of course, electrons are the same thing as the positive charges. So you fill them out as you go along. As long as you keep the rule, the 2, 8 rule, right? So, atoms, if the outer shell is not filled, so if the outer shell is not filled, then what's going to happen? Then they're going to tend to become what? Reactive with other atoms. So until they reach what? The stability, the full electron shell. Now, by doing that, this reactiveness or this reactivity to other atoms is going to cause what? Interactions and or combinations with other atoms and or molecules. And this allows us to create what? In this case, we're creating sodium with chloride together. We call that what? Sodium and chloride, we call it what? Table salt. Sodium chloride is your salt, the salt that you put in food. So what are the different type of chemical bonds that we're going to encounter? So types of chemical bonds, we have ionic bonding and covalent bonding. Okay? In other words, what is happening on the ionic bonding or covalent bonding? The last level, okay, is filled. What last level? What are they talking about, the last level? Right? The highest energy, the outermost shell, right? And that depends on the molecule, on the atom. Now, ionic bonding is what? Losing or gaining a or an electron, correct? The covalent bonding is actually doing what? Sharing. So when you lose or gain, is that somebody takes it away, or you give it away, one of the two. Covalent is actually, there is a union between the two. They share the same electron. So that means they always have to be what? Combined all the time. Ionic bonding, they can be together or separated. Right, so bonds between adjacent molecules, the most common bond that we have is hydrogen bonding. And this is actually the weakest bond of all. So this hydrogen bonding is most likely found where?
Water.
And water. Okay? Now water is a molecule that has what? Surface tension. If you notice, like when somebody, I don't know, falls on a jet ski or on a speeding boat, what's going to happen? Do they actually sink automatically? No, they just go, they just kick on top of the water. And that is because at the speed that you're doing, the water has a what? Surface tension. That's why you don't sink automatically. If there would be no surface tension, then we just hit the water and then sink. In this case, that's not it. Okay? So what is ionic bonding? Ionic bonding, of course, is an attraction between what? A cation and a anion. What is the cation? The cation is the one that donates the electron. So cations donate the electrons. If you donate the electron, do you become more positive or more negative? So cations tends to be what? Positive. Because they donate their electrons. Does that make sense? So I remember a professor of mine in high school, she said, cats are good. So remember, cations are positive for most of the time. The next one is anions. I mean, she liked cats. Anions. Anions are actually what? Electrons acceptors. So if you accept an electron, what does that mean? You're going to become more overall what? Negative. So this is more negative and this is more. All right. And of course, you have properties of sodium. You have the properties of chloride. And then, of course, chloride has what? 7 electrons in its outer shell. So that means that chloride is missing 1 on the outside. So if it's missing, what does it need? It needs to bind to something that gives the relative. So sodium is what? And chloride is a what? You got it. So you have sodium as a cation and chloride as a anion. One overall more positive charge and the other is overall more negative charge because it's an electron acceptor while the other is electron donor. Okay. Do you guys see it? And they form what? Ionic bonding, right? Sodium and chloride, and that's the table salt. Can you live without salt? Can you live without salt? How many say yes? You spend a whole day without eating salt, like no salt in your food? Try to cook your food with no salt and taste it. See how it happens. I mean, what gets into your mind? Like, oh, my life is so bad, right? So we need salt, and actually you cannot live without salt. Sodium and chloride are ions, and they're important in the physiology or the communication between your cells, right? Tissues, organs, organ system, the whole body function. Okay, is how we actually regulate, one of the things that we regulate water. So the next thing that we talk about is the next bond, which is covalent bonding. And covalent bonding is, we said, is what? Sharing. So covalent bonding can be polar or non-polar. What does that mean? Well, when I think about polar or non-polar, I think about polar bears, or that the Earth has 2 poles, positive and negative charge, or north or south pole. So when I think about polarity, I think about a positive and a negative charge. If you guys think about a battery, it's pretty much the same thing. So when you think about a battery, that's a battery, take my word for it. So the battery has a positive charge and a what? Negative charge. That means that the battery has a polarity, right? It's a difference in charges. So when they said polarity, that's what it means. When it means non-polar, it means that it has pretty much the same charge in overall the top or the bottom of the molecule. Does that make sense? All right, awesome. So on the polar one, you have, of course, unequal sharing of electrons. Why is it unequal? Because it will be equal, then you will be what? Right, no charge difference. So if it's unequal, makes that a difference in positive or negative in one end or the other end. A non-polar, it has what? Equal sharing. I mean, if you share the same thing, of course, you're going to get the same charges both throughout. Now, this covalent bonding, it can be, has a charge, difference in charge or no difference. But at the same time, you can bind to multiple things. right? How many of you are bound to a single individual? Boyfriend or girlfriend? Or mom or dad, if you don't have anything, right? So that's a single bond to one person. So single covalent bonding means one pair of electrons. What does that mean? That means that on the outermost shell, right? I'm just gonna do something really simple. There's an electron here and there's another electron here. All you're doing is what? Pairing them up, right? So that's a single bond, a single pair. On a double covalent bonding, what are you doing? Well, there are two electrons on the outer shell, and what are you doing? Pairing. So you're gonna see me drawing something like this or something like that. Okay? You can also have something like triple bonds, right? Means you have on the outer shell, let me just make it a little more weird.
Are they always in the outer shell?
Yes, because the inner ones are just so tightly attracted by the protons, they tend not to go outside, so they cannot react. So it's like, you want to meet somebody, stay in your house. I'm sorry, what? Yeah, if you stay in your house, you're not going to get a job, you're not going to meet anybody, right? And able to meet people, what do you got to do? Get away from hiding. In other words, right? So they are hiding in the center, that's why. So the electrons, again, this one will be 1, 2, 3, and then you have 1, 2, 3. I mean, you get the idea, right? And they're triple bonds. So this is important because actually we're going to spend a lot of time, and that is in DNA. And DNA has double bonds or single or triple bonds, okay? Now, the more bondings, the stronger or the weakest? It makes sense, right? If you're bond with one hand versus two versus, I don't know, the two hands and two legs or the leg or something like that. So it's definitely more bond to it, right? So there's more attraction in this case. The stronger the bond, right? And of course, we have a hydrogen molecule, right? H2, and it shows a double bonding here. Well, in this case, I'm sorry, not double bond, it's a single covalent bonding. Then we have oxygen. This one does show that you have 1, 2, 1, and 2 on the outside. So what are we doing? We're pairing it, right? So that is a double covalent bonding. And then of course we form the molecule of what? What do we use this molecule for? It's the oxygen that you breathe, right? It's the oxygen that is required for every single cellular reaction in your body, right? Why do we use oxygen? Because in order for us to make ATP, which is the energy molecule, it requires that chemical process to use oxygen as part of the starting fuel. Why do we breathe out CO2? Because as a byproduct of almost all the chemical reactions that we have in our body, for cellular respiration, it gives us what? CO2. So we make a lot of CO2 as a pooping, right, of this respiration. So we have to do what? Load the CO2 in the red blood cell and take it all the way to the lungs and breathe it out. So that's why we use oxygen and then release CO2. And they are be traveling where? Where does the oxygen and CO2 travel? What is the car that takes oxygen and CO2? What's that car called? No, car. Like what cell? Red blood cells, right? So red blood cells, right? The function of red blood cells is to transport what? Oxygen and CO2. All right, awesome. And then of course we have the water molecule, right? So water molecule, H2O. So water molecule is of course, molecule. So a combination of two or more atoms, right? By covalent bonding. And then it's also a compound because it has a different kind of what? Atoms. We talked this about already, right? So water serves as both, right? Is an atom. The hydrogen, the oxygen, it serves as a molecule and a compound. Water is extremely important, and that's definitely going to see that on the test. So water has, of course, a covalent bonding, and is actually polar and or non-polar. In this case, the hydrogens are positive. The oxygen tends to be what? Negative. So that is polarity or no polarity? Between the oxygen and the hydrogens, there's definitely a polarity, right? Between the two hydrogens, there's no polarity at all. But most of the time it's between the oxygen and the hydrogen. Okay? So, and of course the attraction of the oxygen to the hydrogen is of course the electronegativity, which is the difference in charges of the oxygen and the hydrogen, right? So opposite poles attract, right? So if you're a good individual, right, what type of people you like? Balanced. According to chemistry. No, I'm just kidding. I mean, you should be attracted to the same thing, but in chemistry, it's different, right? All right. Okay, we have polar, non-polar. We talked about that already. And then, of course, we talked about ionic bonding, right? Just a table summarization, right? We have a sodium chloride, which we said it was an example of what? Sodium chloride, an example of? Ionic, right? Awesome. And then, of course, we have hydrogen bonding. And hydrogen bonding, of course, between hydrogen and is a hydrogen molecule something else, right? So the hydrogen bond is again between the hydrogen and, in this case, the oxygen. It's a brand new, right? So it's a bond of one molecule of water to the next molecule of water. That's the hydrogen bonding. And because of this hydrogen bonding, right, to the adjacent molecules, right, it also allows us to have what? The surface tension, right? So what are the different states of water? So water can be in a form of solid. Everybody knows that. What do we call the solid form of water? Ice. And then the next form is what? How do we go from solid to liquid? You melt the water, right? Okay. So how do we go from liquid to gas? You boil it, right? How much temperature you have to give it in order to boil? Right, it's there, guys, so you have to demonstrate it. So about 100 degrees Celsius, right, water starts to boil. And then which one has, right? No, sorry, let me just finish this one. And then, of course, the last state is what? Plasma. Actually, plasma is not the last state. Plasma is between the solid and liquid part. So let me put that here. So plasma is between the solid and liquid. What does that mean? Have you ever put something on the refrigerator? I mean, on the refrigerator, right? On the ice pots, let's put it that way. And it doesn't quite becomes hard ice. It's just like a jelly, right? Especially if you put shots in there, like jelly shots and stuff like that. If you do the right mixture of, alcohol and stuff like alcohol, it does not get what? Frozen. If it's good. If they temper with, they put water in there and then water freezes, right? So if you have a good alcohol content, then it won't freeze. But it can create a semi-solid state. And that semi-solid state, we call it what? Plasma. By creating this, there are scientists that have got some great results out of it, is that when you actually get water into the plasma state, like this is contaminated water, sewage water, water that has fecal matter and water, when you do a plasma state, they're able to separate the water from the actual solids and plasma. I mean, it's really hard to decontaminate this because we have sewage plants, right? That they put a tank with the solids, right? The solids just float, or they just sink, and then you transfer the water, you put through specific filters, and then you give chloride to the water, and you ionize the water, and all these things. Well, by doing this plasma, you only separate the solids from the water, and you put the plasma in there, and whatever is water can be separated, and whatever is not water, it's going to be separated from the actual water molecule. That's awesome. All right? So, which one is more dense? Which one is more dense? So this is my cup of water. Which one is more dense? Liquid is more dense. Ice is the less density, right? Because when you put ice on the water, it floats. So there's more spaces between the ice, right? The hydrogen bonding versus the one with the liquid, correct? And plasma is supposed to be in the middle between water and the ice, right? And then, of course, then it comes the gas, right? Which is the less dense of them all. Awesome. We got that? So now we're going to talk about hydrogen bondings, right? Water solutions and chemical reactions, which we did a little bit now. So we're just going to go take a deep into the a little more information about water. So we said water is hydrogen bonding, but the hydrogen bonds are important because they do not only happen in water, they also happen where? To maintain the shape of any what? Macromolecule. What macromolecule are we talking about here? Well, this is an example of a linear structure of a protein. So this is linear protein structure. Right. So this is also known as primary, and this is known as secondary, and this is known as an alpha helix. Right. Why are you doing this? Why are you making this so complicated? No, all I'm trying to say is that I want to show you this. The reason why this thing is a linear property is because of the attraction of the oxygen and the what? Hydrogen. When the oxygen and the hydrogens get close together, what's going to happen? You're going to bend it, right? You're going to bend the molecule and you're going to create a hydrogen bonding, and that's going to create a what? A shape form. Going from a linear to a alpha helix, which is just like a staircase, okay? Everybody got that? So that's an example of why hydrogen bonds are important, okay? It creates a secondary structure of the proteins. Now, hydrogen bondings actually are good because they can interact pretty much with any other molecule, and in this case, you have, allows for solubility of compounds. In this case, we have NH3, which is ammonia, right? And where do you actually see this almost all the time? Yes, you're right. Pretty much on everything. Ammonia is, cleaning products, but I will say in your body, every single time. Your blood actually circulates, all the blood in your body circulates a little more than 4 times, right, over the course of a single day through your kidneys. That means that the blood, the majority of the component of blood is water. And water is now diluting everything that goes and ends up in the bloodstream. Because remember, the bloodstream is what takes what? Not only the ions, but all the food, all the oxygen, everything to the rest of the body. So as you filter that in your kidneys are going to get what? Whatever you have in excess in your body. Let's say today you ate, you're supposed to take 2 tablespoons of salt a day, you ate 15. You went into a salty hunt. I don't know, whatever that is, right? So salt. So you ate a bunch of salt, and what do? Well, if your kidneys are working properly, all you're doing is doing what? Yeah. Remember when I said, I like to go to a Japanese restaurant and stuff like that, and you end up going and drinking all the water? So that's what you're doing. You're getting water because your body's thirsty, and it needs some water to do what? To dilute all that extra salt so you can do what at the end? Do both, either pee, right? So because all you're doing is diluting the stuff and peeing it out. So one of the components in your urine is ammonia, as well as ammonium. There's a cleaning product which is ammoniaco, right? Which is, it's actually Latinos the ones who use it, but it's a little bottle. It is ammonium, and it's really concentrated. If you really have a stink in your house and you don't know how to get rid of it, just put a little drop. Okay? If you want to clean a toilet that is really bad, just put a little bit in there and just make sure to use a mask, because the odor is really strong. So the next one that we're talking about is going to be the usage, as I mentioned before, the hydrogen bonding in creating the double helix of your DNA. So the DNA, which is the genetic material found on the nucleus, it is actually, this shape is made by this. By the hydrogen bonding, right, that takes place between these structures. So, what are the 2 major classes? We have inorganic compounds and we have what? Organic compounds. Inorganic compounds, they usually do what? They have no carbon, because organic compounds have what? Carbon. So anything that has a carbon, so carbohydrates, proteins, lipids, and nucleic acids, all are examples of what? Organic compounds. So what is the actual property of water, and why do we care so much? So water is important in our body Because it's about 2/3, that means 66% of the human body is what? Water. Like I said, right? 65% it's water. So I think that's a lot of water, right? I think it's just a lot of water. So a change in body water can have what? Fatal consequences, means into your organism, because now your kidneys will not be able to filter. You'll have too much products, right? Excess products or waste products that you cannot get rid of it. So all that will stay in your body, and that was all it's going to do is contaminate your body, right? It's going to make more toxins. So you need to be able to detox. So most chemical reactions, of course, support life, and that's of course always in a what? Aqueous solution when it comes to talking about our human body, right? About 65%. So what are the properties of water? So you have solubility, right? Why solubility? Because it allows you to do what? Make it soluble. What is that? If it flows like water and behaves like water, it most likely has what? A lot of what? Reactivity. Why reactivity? Because reactivity is by hydrolysis, right? And there are reactions that takes place within the water due to the charge differences, correct? So ions will be attracted or not in the water when it comes to play with each combination of the water molecule. Because things can be water solubles or not water solubles, right? So anything that is water soluble, it tends to be hydrophilic. That means by charges, you're able to mix it with the water. But things are non-water soluble, which is a what? Hydrophobic, like for example, all your fats are hydrophobic. So even though you mix them, you can heat them up, you mix them, it looks like one solution, but when you give it some sort of a temperature change so it becomes colder, the fat would just tend to separate from the actual water mixture that you saw, correct? Like a soup, in other words. Do you know how to take the fat out of the soup? How? Put it in the freezer and just take the top on top. But if you don't want to get the whole soup to become cold, all you got to do is you get one of those big spoons, right? You put it in the freezer. Once it's really cold, you top it on the top of the soup, and then it will collect most of the fat that is on top. All right, you can do this a series of amounts of time. So high heat capacity. Water is able to withstand what? Heat. That means it's able to absorb a lot of heat in it, right? Up to what? 100. 100 what? Degrees Celsius. All right. So, and that's also, water is a good what? Lubricant as well as cushioning. And that is the example of our cerebrospinal fluid. So our CSF, which is cerebral, means brain, spinal means spine, and fluid is because most of it is water. It's surrounding our brain, surrounding our spine, and allowing it to do cushion, but at the same time to provide for lubrication, plus other things that we're going to talk about that later towards the end of the semester. So aqueous solution is allowed to do what? Well, if you're going to do a solution of a lemonade, how do we do a solution of lemonade, guys? Solution of lemonade. So inside a solution, there is a what? A solvent, and there is a what? Solute. The solvent is the major compartment. So how do we do a solution of lemonade? Thank you. Lemon and water. That's it. That's water with lemon and sugar. Thank you. So which one will be your solute? Solvent is the biggest part of it. So the solutes will be the lemon juice and the sugar. You get it? And the water will be your what? Which is what allows you to dissolve both solutes. Everybody got that? So a small part of it are the solutes. In able to dissolve it, you got to put the solvent, which is in this case the water. Okay? If you make Coca-Cola, right? How do you make Coca-Cola? What is the solvent? Water. What are the solutes? Coke leaves. No, it doesn't. They used to do that. Actually, Coca-Cola got the name because of Coke leaves, right? Coca leaves, right? Coca. Yeah, it came from coca leaves. I don't know if it had cocaine. Coca leaves is a tea, right? I had the tea. It's I don't know. It's a tea. It doesn't make you go wild or anything like that. It's just a tea. Coffee makes you go wild than coca tea. Anyway, by the way, that's the plant, right? This is the leaf. All right, just in case you guys were wondering what type of tea. So, and then of course the rest of it, Coca-Cola, is what? Sugar. So I think it's about 3 tables of sugar per 1 of water or something like that. That's what it is. So that's how much sugar that Coca-Cola has. If you don't believe me, look at YouTube, and it's awesome. What they show you. There's so much sugar in there that it's crazy. So then, of course, since we talk about the solution and the solvents, right? All what is happening inside when you're mixing, doing that mixture between the solvent, attractions between the water molecule, and since the water molecule is attracting to both the sugar and the lemon juice, all you're doing is pulling that up, and water is going to start to break in between those, and water is going to bind to a chloride, well, to a lemon juice or to a sugar molecule, all right? And in this case, it's going to start to do what? Separate or dissolve, right? The solids that you put in there, okay? Just by attractions, okay? Of course, you can see, right? The sodium, which is negative, goes to the oxygen, and then the chloride, which is positive, right, goes to the hydrogen, etc. All right. Then all we're doing is what? Every time that you make the whole solution, all you're creating is what? Hydration spheres. So just make sure you know that. So when you're doing a solution, all you're doing is hydration spheres. All it is just getting the solutes and paired or surrounded with water. That's it, as you mixed it. Skipping over all this. No, same hydration spheres. So water can allow us to go now into mixtures. So mixtures that get substances that compose of 2 or more physically intermixed components. So we have a solution, which tends to be what? Homogeneous mixtures, and pretty much about the same. And you have colloid, which is something that is what? Heterogeneous. Hetero means what? Different. So it gives you sort of a milky, okay? Cerebrospinal fluid is one of those. Lymph is another one, and your blood plasma, it's another one. So whenever they talk about blood or blood plasma or retrieving blood or taking blood from a patient, they're talking about what type of mixture? A colloid mixture, okay? The next one is suspension. A suspension, of course, it is the same thing. It's heterogeneous mixture, but it has a large, right, visible particles that, what do? They settle out. Have you ever seen things settling out? Now you need to know that blood is what? A colloid and a awesome. That's all I care about. So hydrogen bonding, right? As mentioned before, we have those hydrogen bonding. We talked about this already. And we actually mentioned about hydrophilic and hydrophobic compounds, right? So if something is hydrophilic, it will dissolve in the water. If it's hydrophobic, it most likely has a lipid component to it. So it will not dissolve in water because of the reactivity of the charges. So hydrophilic compounds, again, is your sodium and chloride, so in this case, your salt, as well as alcohol is able to dissolve good in water. But then a hydrophobic compound, like for example here, oil or methane, right? As you can see here, an oil spill in the ocean, it actually can be separated by, eyesight, right, on the ocean. And that's one of the biggest things that we have, since we have so many oil rigs in the middle of the ocean, right? This is a pure contaminant, not only to the ocean itself, but to the fish and to our life, because we depend on it. How many of you eat fish? Right. Okay, so the whole purpose of this is to take you all the way to a phospholipid. So a phospholipid is a structure, or is the structure of your cell membrane. So on the cell membrane, that phospholipid will have a hydrophilic head, means it dissolves in water, so it's good with the water. And it has a hydrophobic tail, so this is a what? The lipid part of it, right? So one, it has the water compartment, and the other one does not. So polar head, non-polar tail. When you see the cell membrane, it's going to look something like this. So this is the outside of a cell, and this is the inside of a cell. And then you're going to have 2 and 2, 2 and 2. So it looks something like that. So the lipid aspect of it, it will be in the middle. And the water component, or the phosphate heads or polar heads, are going to be on the outside, right? So this is the hydrophilic part. Because again, inside the cell, you have a structure known as a cytoplasm, and that is a water component. And outside the cell, you have our body, right? Which is, most of it is just water component, which is known as the extracellular fluid and or space. Now, the phospholipid, of course, you can see the actual orientation here, right? The one that I draw. But of course, that one is prettier. Now, that means that what things are allowed to go through that cell membrane? Anything that is hydrophobic can go through, correct? Anything that is hydrophilic will just bounce back. Okay? That means hydrophilic, it will not prevent the extracellular fluid to enter directly into the what? Intracellular fluid. That means if you eat something, or if you have too much amount of water, you're not going to get all that toxins or all those things into the cell directly. It may require specific structures, and the structures that allow hydrophilic particles to go through, those are known as what? And I'm just trying to draw here, all right? These are called what? Channels. What about channels? Well, channels are, a channel, it's a door. So these channels can be open, and do you see any door between them there? No, it's just an open space, right? From one end to the other. But only specific things can go through there. In this case, will be hydrophilic compounds. These channels can have a door, both on the inside and on the outside. That means for it to open, it may require what? Electricity, all right, ATP, or other structures. So you provide energy to it, the door, all it's going to do is going to do this. It's just going to open up so things can go in. The inside door is just going to open up so it can flow all the way in. Does that make sense? So these are channels. You're going to see me talking about channels soon. Now, the hydrophobic ones, since they, in the middle, it's all lipid, they can go freely through the cell membrane. If you have any particles that are really small, and if you think about it, I don't know, if you look from the top, there is a space between this and another one just like this one, right? So there's a space here in between it. I know it's really tiny. So imagine that you're looking at a mesh. You're looking something like this from the top. So inside each one of these things, there's a space. So if the molecule is big enough, it's going to be able to pass through the what? Through the space in between, from top to what? To bottom. So if the molecules are small enough, they can go through again. So what things can go through the cell membrane? Lipid and small molecules. Okay? Water can go through, right? Sodium, chloride, not all of them, but they can go through in certain part, or any lipid molecules. So what are the chemicals reactions? So in chemical reactions, since now we're talking about molecules and coming in and coming out, there are reactions that are going to take place in our body. So you're going to have a decomposition reaction, which is known as what? Catabolism. And you're going to have a creation or a synthesis reaction, which is known as a what? anabolism. And most of you guys heard like, oh, you're in catabolic state or you're in anabolic state, right? When they say, oh, anabolic steroids, what do they say about anabolic steroids? Anabolic means what? You're creating, right? Anabolic steroids creates muscle mass, creates tissue, right? That's why they say anabolic. Okay? When you're in catabolic state, what are you doing? You're breaking down. How many of you have had breakfast today? 1, 2, 3. Right. How many of you have not eaten anything since, I don't know, 10 last night? You are in what? Anabolic or catabolic state? You're in catabolic state. All you're doing is breaking down the glycogen stored in your livers. That's what it is. You're just breaking out of those glycogens. All right? Now, you also have an exchange reactions and reversible reactions. And reversible reactions are reactions that can go one way or vice versa. So, chemical reactions, let's talk about this ones. So, normally the reactant is on the left and the product's on the right. I'm not going to ask you anything specific about the reactions. I'm just going to show you what that is, right? So, ethanol, which is another form of alcohol, when it binds to the oxygen, it creates what? Acetic acid and water. What do we have? A product. What are these two? Reactants. It doesn't matter what the name is. I understand that you're not supposed to know this, but at least know to identify a reactant versus a what? A product. Okay? So a decomposition reaction, what do? You get a large molecule and you break it down into what? 2 or more smaller ones. Correct? Now, a synthesis reaction, you get small molecules and you combine it and you make a larger molecule. And then you have an exchange reaction, which is 2 molecules, right? Exchange, and they creates a group of atoms. So I'm going to give you an example of those things. When you decompose a reaction, well, decomposition reactions, this is the example of creating what? ATP. Why ATP? Well, if we think about it, we are using the glycogen that is stored in your liver, right? So that glycogen stored in the liver is going to be broken down into glucose. And then glucose is going to be used by your mitochondria, right? Plus oxygen to create what? ATP. And that's what can allow you to be alive for about 8 to 12 hours and even more. But that's the average. The glycogen stores that you have in your liver will last about 8 to 12 hours. Unless you train your liver and you can actually get more out of it. Okay? Then after that, all you're going to start is breaking down what? If you fast for greater than 12 hours, what are you going to start breaking down? Come on, guys. Everybody knows this. Fat. Your love handles, right? So when you start fasting over 12 hours, all you've done is you already use all the sugar possible in your body, and now you're just breaking fat down out of your body. You're just melting the fat out. Okay? So hydrolysis is just breaking down the molecule of what? So decomposition reactions, lysis, is by this case, we're doing here, we're getting a dimer, which means whatever this in here, we have an enzyme, we have the water, and then we break the molecule of water, right, which is the h2o, and then the water is going to be separated into what? OH and another H, which is you have H2, right? So one H goes here, the other H goes here, right? So H2, and then one OH or one oxygen goes here, and the other one just binds to the other oxygen. Okay? Synthesis. Synthesis is creation, right? So when you're doing a synthesis reaction, you're getting amino acids. What do you get amino acids from? From the food, right? From the proteins that you eat. So if you're getting all these amino acids, all you're doing is you're breaking these proteins down to simple amino acids, and then you can reassemble these amino acids and create something that is required in your body. Okay? And that, of course, is creation of new proteins. And proteins are built by groups of what? Amino acids, and amino acids are linked. Right, this tiny link right here, this tiny link is known as what? Peptide bonds. So proteins are made by what? Amino acids, and amino acids are glued together or linked by peptide bonds. Everybody got that? So what's the crazy glue between the amino acids? Peptide bond. I said crazy glue. Just remember something that you usually use, right? Because that's the attraction that takes place. So what is a reversible reaction? Reversible reaction is a reaction that actually can go either one way or another way, right? Well, it's supposed to be one way, right? Forward or backwards, right? So reversible reaction means, for example, of carbon dioxide and water. If you get the carbon dioxide, you get CO2. So you get CO2, and then you're missing another oxygen, right? That's plus an oxygen. What is the oxygen there? Well, this oxygen comes from where? Water. From the water. So hence we have what now? CO3, right? All three oxygens. Now, the H2, well, H2 comes from where? From the water, right? So you have H2, and the C, well, comes from here. H2, CO3. So that's what happened. Now, this can actually move what? Forward, creating H2CO3, or H2CO3 can actually go into a decomposition or just reversible reaction into what? CO2 and H2O. Okay? And by the way, carbonic acid, this is the main way that you transport your CO2 to the pulmonary system, so you can breathe them out. Remember we talked about that every single cell reaction has CO2, right? Almost every single one of them. And most of your body is water. So when you dilute the CO2 on the water, you create carbonic acid. And that gets transported all the way into the lungs. And at the level of the lungs, it goes backwards and it separates the water from the CO2. And you're able to breathe CO2 out. Hopefully you don't breathe that much water out. Do you breathe water out? Yeah. I mean, if you think about it, you breathe, you actually feel this humidity, right? So as you breathe out, you also lose water. Okay? Organic compounds. So organic compounds, for example, carbohydrates and lipids. So what are organic compounds, right? You have carbohydrates, you got lipids, you got proteins, and you got, of course, nucleic acids. Where do you find carbohydrates? Which foods? You find out all this in the food. Bread, rice, pasta, cereal, right? You get the point. All right, awesome. Lipids, fats. Well, I don't know what that is. Do you eat fat? Meat, because the meat has a lot of fat. What else? Oil, butter, cream cheese, avocados, fried, whatever, right? All right, so proteins, muscle, proteins, nuts, beans. Yeah, it's a small amount, but yeah, you find there. Nucleic acids. Nucleic acids. Nucleic acids, DNA. What? Well, which things have DNA? Well, yeah. Yeah, pretty much all that. What about, I don't know, what about tomatoes? Do you get DNA in the tomato? Yeah. Well, by definition, is anything that has a cell must contain a what? A nucleus. And anything that has a nucleus should have inside what? Awesome. So if you eat anything that has a cell or is composed of cells, guess what? You get nucleic acids. Awesome. So let's go into those. Now, the first one is carbohydrates, right? So carbohydrates is carbon, hydrogen, right? I'm not gonna talk about the functional groups or anything like that. Let me just skip over this one really quick. So carbohydrates, and carbohydrates comes in different flavors. Carbohydrates are made out of carbon, oxygen, and hydrogen. So that's hence the name hydrogen or carbohydrates, right? Carbo, oxygen, and hydrogen. Now the carbohydrates can be in a what? Monosaccharide form means only one. A disaccharide form means what? Two. Or a polysaccharide, which you have more than two, right? A monosaccharide is one that we're going to talk about. And well, they can be poly, but poly can be trios, tetros, pentos, hexos, or heptos, which is as many as you can put in there. All those are part of polysaccharides. So carbohydrates are complex what? Carbohydrates are just what?
Sugar.
They're just sugars, right? Carbohydrates are just sugars, all right? So monosaccharides, right? Let's talk about monosaccharides. Monosaccharides, well, it's made out of a pentose, which is a 5-carbon atom or a 6-carbon atom. Hexose. The pentose sugar in this case, so the sugar portion of your DNA. Oh yeah, your DNA also has sugars in there. What, sugar in DNA? Yeah. So the DNA has deoxyribose, hence the name D. So D for deoxyribose. And the RNA has what? Ribose. And let me write that down. So this is known as deoxy. Oh, well, I don't even know how to write. Deoxyribose and ribose. That means which one is the sugar, the ribose or deoxyribose? If you all have a DNA, it's deoxyribose. If you all have RNA, it has ribose. So even in the DNA, you have sugars. So the DNAs are composed of a sugar, deoxy or ribose. It also is made out of what? Nucleic acids. And what else?
Phosphate.
And a phosphate. Okay? Back on. So let me just give you the example of monosaccharides and disaccharides. So what are monosaccharides? Your monosaccharides are going to be what? Glucose. I know it says disaccharides there on top, but your monosaccharides is glucose, fructose, and galactose, the three that I just highlighted. So glucose, fructose, and galactose. Where do you get glucose from? Sugar. Sugar from where? Artificial? No. Just plant sugars, right? But what about fructose? Where does that come from? From a fruit. Wait. A plant? A fruit is not a plant, right? A plant gives off a fruit. This case will be sugar cane, right? But again, sugar cane is just a combination of both. So that's a disaccharide. So a fructose comes from fruit. So if you're trying to get a keto diet and you're eating like 3 or 4 fruits in a day, that's not good because you got a lot of what? Sugars in there. So what is a disaccharide? A disaccharide, I'm going to do a different color. A disaccharide is 2 what? Monosaccharides together. So sucrose, which is your table sugar, the sugar that we use all the time, is just a molecule of glucose plus a molecule of what? Fructose. Okay? The next disaccharide that we have is maltose. Have you ever drank malt? Like malt liquor, malt beer, right? Like Malta?
Yes.
So that's really sugary, right? And that's how I remember is double shot of sugar, glucose, glucose. And if you look at it, you're always going to have glucose in all the disaccharides. Now, the last disaccharide is going to be what? Lactose. And lactose is what? Found in the what?
Dairy.
In the dairy products, right? Especially milk. So galactose plus the same molecule, right? If you look at it, we're doing what? glucose, glucose, and glucose all the time, right? So glucose is always found. Now, that's going to give you pretty much found in all these products. So monosaccharides and disaccharides. As you keep building up, you build up to, after the disaccharide, you build what? Your polysaccharides. So now your polysaccharides are known as what? Complex carbohydrates. Have you ever had a potato? Yuca? Pumpkin? What are those? Complex carbohydrates, right? We call them what? Starches. Starches, all right? So these polysaccharides are what? Starch. They can come in a form of what? Glycogen. Cellulose. Say what? Cellulose? Like where does your cellulose come from? Cell. But where do you get cellulose from? Plant cells. Chitin. Where do you get chitin from? Where do you find chitin?
Invertebrates.
All right, we're going to talk about chitin. And what about fibers? You guys know you're supposed to have a well-balanced diet with fibers, right? What type of fibers do you guys like? The one that tastes good. Yeah, those are none. In order for them to taste good, you got to put a lot of sugar or something in it, right? So fibers can come in two flavors. It could be what? Soluble or non-soluble fibers. Which is the one you want? Solubles, right? So they can get into your body, absorb, and now you get more fat. No, you want the non-soluble ones. The non-soluble ones are the best ones. I mean, both of them are good, but the non-soluble ones are the best ones, and all they do is they create a bulk, right, in your fecal matter. In other words, it's going to allow you to move the waste products that you have eaten. So increase the lifespan of your GI tract. Let's talk about those. So starches like what? You got potatoes, glycogen. Let me just go over this one. So glycogen is actually in the forms of what starches do, right, in the plants. So starch comes in the form of what? Starch in a... Do we store starches? No, we store what? Awesome. All right. And then we have cellulose. And of course, cellulose is what? Plants. And then chitin that we talk about is a rigid complex carbohydrate, which sometimes it makes, well, most of the time it makes the skeleton of insects, spiders, right, crustaceans, as well as, of course, one of those is example of crabs, right? So all those arthropods, right? And then we got fibers. So soluble fibers versus insoluble fibers. So soluble fibers will, of course, dissolve in water, and insoluble fibers do not dissolve in water. And you can see there which are the insoluble fibers and some examples of the soluble fibers. Okay. Lipids.